Example 8.17, page 157 in your textbooks. So here we have a sphere of weight W and radius 50 centimetres hanging by a string 80 centimetres long, attached at one end on its surface to a smooth vertical wall. And we're looking to find the tension in the string and the reaction at the wall in terms of W. So if we take our diagram and we draw it, what we can see is we have the centre of the sphere marked in. Because it's in contact with the wall, we're going to have our reaction force. We're going to have weight. And we're going to have tension acting away from the body. But by Theorem 7, we know that these three forces acting on the body must be concurrent. In other words, acting through the same point. Now, if we mark in those distances on our diagram, we have the radius is 50 centimetres. And we have the length of the string is 80. So if we complete that triangle, what we notice is our favourite triangle, one of our Pythagorean triples. By adding 80 and 50, we're going to get 130 centimetres. And here we have 50 centimetres. So by completing Pythagoras, we'll end up with the opposite side being 120 centimetres. And of course, if we look closer at that, we see that that's our triangle, 12, 13 and 5. This then allows us to mark in the opposite, the hypotenuse and the adjacent. And of course then what we can get is cos A is equal to the adjacent over the hypotenuse, which is 5 over 13. And we can get sine is the opposite of the hypotenuse, which is 12 over 13. So if we're looking to get tension in the string T, we can see clearly that T is not going to apply to any of our laws because unfortunately it's not an up or a down force or a left or a right force. So instead what we're going to have to do is we're going to have to resolve the vector T. So again, remember to always take a different colour when resolving your vectors or use broken dotted lines. So I'm going to draw our parallel component and our perpendicular component. And of course, if we look at these two lines here, they must be parallel, which means that if this is the angle A, this is also the angle A because they are corresponding angles. So therefore this makes this one here the opposite, which is going to be T sine A. And this one will be the adjacent, so it'll be T cos A. So if we apply our first law, we're going to say our up forces equal our down forces. And we can see then that our up forces equaling our down forces must be T sine A equals W. But of course, sine A equals 12 over 13. So that becomes 12 over 13 times T equals W. And straight away, we can see then that T must be equal to 13W over 12. Really easy. And we've solved for T. So if we apply our second law, we'll be looking at our left forces equal our right forces. And here we can see that we have the reaction force must equal T cos A. And of course, cos A is equal to 5 over 13. So by applying that, we end up with or must equal T cos A. So the reaction force at the wall must be T times 5 over 13. But of course we've just solved for T, and we know that that is 13W over 12. And if I multiply that by 5 over 13, then we can see that our 13s cancel, leaving us with or must equal 5W over 12. And there we have our reaction force at the wall and also our tension in the string. So we're going to have a look at some exam questions next then to see how complicated these questions can get, but of course always bringing it back to Theorem 7 and our 3 laws where possible.